before we start the video, let me give you a brief introduction about myself. I'm Chandresh Mahajan, who is founder and chief educator at Exergic, which is India's most trusted and comprehensive institute for online gate preparation. I got an All India rank 37 from Gate Mechanical Engineering, and I am an ex Indian Oil officer, having 6+ years of teaching experience as of now. To know more about our GATE courses, you can contact us on these details. Also, you can download Exergic GATE preparation app from Google Play Store. The link is available in the description of video. Now let us start discussing about shear center. And before we begin that discussion, let us develop some fundamental concepts of shear center, how it comes into action, and all the other fundamental concepts that we need to fully understand shear center. So let us develop and build those concepts first. So right now we are going to first discuss about the concept of shear flow. The concept of shear flow. What exactly is shear flow, how it comes into action, and how shear flow then affects the phenomena and the origin of shear center, that we will discuss further. So these are the concept of shear flow. Consider this to be the fundamental of shear center. Without understanding it totally, you cannot actually understand why and how shear center is coming. Okay, so I have drawn so many diagrams here, right? But all of them are going to be very important. Each of them is going to be very important, and I will discuss them one by one. So don't try to look at all the diagrams at once. Just focus on one diagram at one time. Okay, focus on this diagram here. What can you see here? You can see that this is a fixed end, right? This is a beam, a cantilever beam, because a load of P is acting on its free end. So a cantilever beam, this is the fixed end, and a load of P is acting here, right? The cross section of this beam is an I section. We already know what is an I section, where the section looks something like this, right? We have already discussed about why we use I section, what is the importance of I section, in which industries it is used and why. So everything we have discussed already, right? So this is how roughly the I section is going to look. The three-dimensional view of that I have shown here. Now notice that in this diagram, in this complete beam, I have highlighted only a small portion AB here, right? Using blue dotted lines, I have highlighted this region. This is the only part of the beam which we are going to discuss right now. Let us take only this part and remove the rest part of the beam. We are not concerned about that. We are only focusing on AB part currently. Okay. I have shown that AB here in 3 dimensions. This A basically, please note, is not a single point. A is complete section, complete cross section I am calling as A. And this complete cross section I am calling as B. So between A section and B section, these are two parallel sections, right? Along that, between these two sections, the beam, the part of the beam available, that I have shown here. So please note that A is not specifically this point or B is not specifically this point. This whole area, this whole section, cross section is B, complete section. And at that part, at the back part of it, that complete section is section A, right? Same is true here also, everywhere. I will talk about all of them one by one. Now, in this beam, in this particular beam, it's a complete beam, complete cross section I have shown. Only consider a small section of that. Only, let's pick only this section of the beam. Please carefully watch and listen to everything that I am telling here. So out of the complete beam, I have only selected this small portion here, right? It's going to be a cuboidal section. So only that section I have picked and shown here. This part here, this part is shown here, and that same thing is shown here in 3 dimensions. Please note that it is still a part of B section, and the back part, this one, is going to be the part of A section. So this area is a small area of the complete B section. That area will be a small area of the complete A section. So when I am representing this part here, I have written it as B. This small part is a part of this complete section. This I am writing as B, and this part, which is the part of complete area A, I am writing as A. Clear? So this same diagram I have drawn here in 2 dimension. Now, come back to this original diagram. We very clearly know that in such cases, 2 types of forces are going to act, or 2 types of load are going to act. 2 types of resistance will be developed in section A and section B. Which will be those 2 resistances? Shear force resistance and bending moment resistance, right? Because the cross-sectional area of this beam will resist this P load in 2 different ways. The area will generate a resistance along its area, along its dimension, which is the shear force. We already know what is the shear force, right? So that force is shear force. And when it generates the forces perpendicular to the area, they collectively form a moment which is bending moment. Now, these are some of the basics that we have already thoroughly covered, right? So shear force and bending moment, these are the 2 types of resistances, 2 types of resistive load that will act on section A and section B. Is it clear? Now, the amount of resistive moment, let's focus only on that. Let us now focus only on resistive moment. Why? Because we have already covered the variation and the discussion of shear force. The shear stresses in beams is a separate unit in itself, where we have discussed about how the shear stress is going to vary for any of such transverse loadings, right? So right now we are not discussing that. Right now let's take only the effect of bending moment. Let us only consider bending moment right now. And we know that why bending moment comes into action, because there is a pair of tensile and compressive loads at this cross section. We know that if such a force P is applied, above the neutral axis part will be in tension, and below the neutral axis it will be in compression, right? So this part here, the upper part, is going to be in tension, and the lower part is going to be in compression, right or not? Similarly here also, upper part will be in tension like this, lower part will be in compression, right or not? Suppose this is the neutral axis. This is the neutral axis. So above that it is tension, below that it is compression. But will the tension and compression be same for section A and section B? No, because we know that the bending moment will increase when we move towards the fixed support. At section A, bending moment will be P multiplied by this distance, P multiplied by X. For section B, bending moment will be P multiplied by this complete length. This length is more for B and less for A. So bending moment at B will be more than bending moment at A. Bending moment at B is more. It means that these loads and these stresses which are shown, they will be more, they will be higher than they are at this point A. And this is what? This is something that we already know, that at this section bending moment will be higher. Why bending moment comes? The bending moment is a resultant force, is a resultant moment of all of these normal forces generated at the section B. Section B, section A, both will have tensile and compressive forces. The collection of those normal forces, both tensile and compression, are normal forces. The resultant of those normal forces is bending moment, right? I am sure you know these variations. We have already discussed about these variations. The shear force is separate, but the normal forces, their resultant is bending moment, right? So this is what we are talking about, only bending moment. So these tensile and compressive forces collectively form bending moment. The bending moment at B is more than bending moment at A. So these stresses or these forces which we are showing, the tensile stress and the compressive stresses, will be more at section B than they are at section A. This is important to recall. Now, you can clearly see here that what I have done, I have only selected this section here, this section. Please relate this with this part. At section B, in the upper half, there will be tensile stress which will be moving out here, moving out of the normal area, right? And on the lower half, there will be compressive stresses going into the area. Similarly, on the back side of section A, there will be tensile stresses moving out from the normal area, and in the lower half, compressive stresses moving into the normal area, right? If you look at only this part here, tell me what type of stress is going to act. What type of stress will act in this section, in this fiber that I have considered? Tensile stress. For this case, it is in that part which is going to get tensed because it is above the neutral axis for such a loading. Again, these are some concepts which we have already covered. So this part and that part, both this area and that area will be under tensile stresses. But the value of tensile stress here and there will be different because it is section B. It is section A. We know that at section B the stresses will be more than they are at section A because the net bending moment at B is more than the net bending moment at A, right? So if I only show this cuboidal section here in 2D and in 3D, you can very well understand that the stresses acting at section B will be more than stresses acting at section A. That's why I have shown them with larger lines. The stress lines of sigma 1 which is acting here are more than sigma 2 which are acting at A. Same you can see here. These lines are more than this line. This is a 3-dimensional view. This is a 2-dimensional view. The value of shear force for this diagram will be decided by this area. And for this case, it will be decided by this volume. Again, some of the concepts that we already know. I am just recalling them here. Okay. Now consider only this section as free body diagram. So this free body diagram you can consider, or this free body diagram you can consider. If you consider this section as a free body diagram, you will realize that the forces, the resistive forces, normal forces are not balancing each other. Area is same, but stresses are different. So the net force in this direction F1 will be more than the net force in this direction, which is F2. F1 is not equal to F2, so there will be a resultant force in this direction. Right or not? And this F will be F1 minus F2. Now let us assume that the difference of F1 and F2, which is this F value, suppose this value is 15 units. I am using a number here because it will be easier for us to discuss things ahead because we are going to consider many more sections further. So if it will be in the form of numbers, it will be easier for you to understand. So suppose on this small section, this one here, the net force acting along the longitudinal direction due to difference of normal forces is 15 units. If I look at the top view of this section, top view means this part here, this whole part is the top view when you look at it from the top. So this is how it is going to look. Again, I will just take few moments to explain A and B here. Since I have written B here means this complete section is B. I have written B here means this complete section is B and this complete section is A. So in this diagram, if you look at this diagram from the top, these are your eyes. If you look at this beam from the top, you will be able to locate A section and B section. The top surface of that section I have shown here. Is it clear? So now you can relate this diagram, this one and this one. Here also, if you look at it from the top, then the area that you will be able to see, this I have shown here. This section is B, this one, and that section is A, this one. We have considered this fiber here, right? This fiber here. Here, everywhere. Right now we are talking about this fiber. So this is the fiber that I have highlighted using dots. Correct? This force, this is the dotted part. The dotted part that I have shown here is this one. In this diagram, it is this one. This dotted part, right? The resultant of them, F1 minus F2, which is F, which is 15, it is acting along F1, along the larger value. So here also F1 minus F2, the resultant of that will act in the forward direction, in this direction, F15. Here also it will act in the forward direction, here. 15. Only for this block, this fiber, this cuboid, we are considering it, right? Now tell me, since this whole beam is in static equilibrium, so section AB will also be in static equilibrium. If any section, any body is in static equilibrium, we know that each and every part of that section will also be in static equilibrium. If a body is in static equilibrium, take any part of that body, no matter how small or how large, it will also be in static equilibrium. The concepts that we have discussed in mechanics, right? And we have also used this concept throughout strength of materials. So if this whole beam is in static equilibrium, this cube or cuboid or fiber will also be in static equilibrium. It means that if normal force is acting, if I show that section here again, if normal force is acting on that section, F1 and F2 are making a non-zero resultant, are giving a force F in the forward direction, some part of the beam has to act to provide a force F in the backward direction so that it gets balanced. What part of the beam can do this? The adjacent part of the beam, which is in contact with it, the surface on the other side. So let me explain that using this particular box here. Consider this is the first fiber that I discussed. This is the top view. This is the cross-sectional view. Okay. And now the force F1 is acting here in this direction. So this tip of the marker, assume that it is the arrow. Okay. So this is the direction of F1 in this way. F2 is going to act here in the opposite direction. Since F1 is more than F2, so net force F is going to act in this direction. Now this net force F on this fiber, consider this to be the free body diagram. So on this fiber, this force F, net force F, due to the difference of F1 and F2, needs to be balanced by one more F force of the same magnitude but in the opposite direction. And where it is going to act? On this surface. This is the surface which is contacting the adjacent fiber. So the rest part of this cross section will exert a force F in the backward direction on this fiber. And where it can apply that force? On this area through which it is contacting, through which both of them are contacting each other. So the resultant F, which is 15 units, will be opposed by a shear stress of 15 units in this direction. On which area? On that area which is contacting the next fiber, on this area. On the top view, this area, right? On the cross-sectional view, this area. And in reality, this is that area. So F force is going to act in this direction. Now, this highlighted part here, which is the section on the other side, on this side, this section here. I can show that to you in this diagram, this section. Can you imagine this section? The top view is going to be this line which is joining this fiber to the adjacent fiber. This surface, this surface, this surface, all of them are same. I hope you are able to imagine this. So on that surface, the next fiber which is going to be here, that fiber will exert a shear force in the backward direction of net force F of 15 units. So the shear force that will be experienced by this cuboid will be in the backward direction. Here, if I want to represent that, where will that force F be felt? That F force will be felt in this backward direction. Please consider only the free body diagram of this fiber. I am only considering this fiber here. So F1 minus F2 have a resultant force in the forward direction that will be balanced by a shear force in the backward direction of the same magnitude on the opposite direction applied by the adjacent fiber. Now note that this F is a shear force, right or not? Now recall the concept of complementary stress. From the concept of complementary shear stress, we know that if shear stress or shear force is acting in this direction of any element, of any cube, it has to get balanced by a shear force on a perpendicular plane in the opposite sense, which is trying to rotate it in the opposite sense. Only then it can maintain an equilibrium like this 2D element which we have shown and discussed a lot of times. So if on any given surface shear force acts in one direction, on its perpendicular surface it will act such that it is trying to rotate the element in the other direction. Again, this is something which we have discussed already. Let's recall the concept of complementary shear stress. A force F in this direction needs to be complemented by a force of same magnitude but acting on perpendicular area like this. So the force of 15 Newton in this needs to be complemented or needs to be balanced by another force F which is acting in this direction. So this is the final direction. This is the final direction which is normal to this area on which F of 15 Newton was resisting. So this force will be complemented by this force by the concept of equilibrium, and this is the final value and direction of shear force. This is the cross-sectional view. Please remember, this is the cross-sectional view. This is the top view. So this force of 15 Newton is going to act like this. So the shear force that I am talking about will come on this surface, right? The surface along the whiteboard. This is the same value of force F which I have shown here. This F force and this F force are exactly the same. From the top view, if there is a force F acting here, from the top view it will look like this, and from this view, from the cross-sectional view, it will look like this. And this is the complementary shear stress or the force which is acting on the other surface, on that surface which is adjacent to the fiber, on this surface which is also F, which is the resultant of F1 and F2. Now let us add one more fiber to this discussion. We were only discussing about this fiber, this cuboid. Let us add one more fiber. Let's have a look at other views. It will give you a better idea. We have added one more similar fiber to it. So I have dotted one more fiber here. On the top view also, only this region was dotted, and now a similar region adjacent to it is also dotted. So another region I have also dotted. And here, just like we are having one cuboid, another cuboid will be added. The same exact dimensions will be replicated, will be doubled. And now tell me what is going to happen. Sigma 1 will be present there also, sigma 2 will be present here also. With the width of the beam, we are not considering any change of the stresses, of the normal stresses, right? So the sigma 1, sigma 2 exact will be replicated on this adjacent cuboid also. So F1, F2 will also come because area is also same. F1 and F2 will come, so resultant force of that particular one will also be F, which is 15. So 15 units force which was generating as a difference of F1 and F2 will be exactly replicated there also. So now if I consider this as the combined element or the combined fiber, obviously sigma 1, sigma 2 will be there also. I have not shown it, but sigma 1, sigma 2 will be there also. So tell me how much will be the value of F now. Value of F will double. It will become 30 from 15, right or not? Here also, if you look at the net force here and here, this is F1, this is F2. For a single block or for a single fiber, it was 15. For the exact same fiber with the exact same loading, it will double. It will become 30 now, right or not? So if that force F, this force F has become 30, what is going to happen? On the adjacent fiber, suppose this is the fiber initial one, this fiber is this one, and then this is the next fiber. So on the adjacent surface, on this surface, a shear force will be acting which will balance this force of 30. If this was the initial fiber, this one, this is the another fiber, so the net force that they are experiencing is F1 and F2. The difference of F1 and F2 collective is now 30 units. 30 units is the difference of the normal forces. To balance that, another 30 Newton of shear force will act on this part, on this fiber, in the backward direction, right or not? And that will be generated, that will be coming in this direction also, on this surface also. Just exactly the same like it was happening in the first case. Here also exact same thing will occur, exactly the same. The only difference is that now the force is doubled. So on this surface, the force that will act will be 30, not 15. It has doubled now. So you can very clearly say and conclude that for this part, shear stress or shear force is varying linearly. And that's how it varies. It varies linearly till the center. If this is the I section, and I want to see that how this shear stress acting on this part, on the flange, is going to vary. It varies like this. You can see that it linearly increases. If we conduct this same analysis from here also, you will conclude the same thing, right? The same analysis which we have done. We have started from a section which is present here. If you start the same analysis from there, from this end, you will conclude the same thing, the same variation you will conclude, linear variation. So the value of shear stress or shear force that will be felt here, the collective one is going to increase. That will become 30 now, right? Same is going to be the story here. If you repeat it here, same thing is going to happen here also. You can see that in both of these cases, the shear force acting is acting in two different directions. It is not flowing in a single direction like this. You can do this analysis, you can imagine this analysis, ultimately you are going to conclude the same. So they are, in a way, you can say that it feels like that they are originating from here, they are moving in that direction, right? This value is higher, this value is 30, this is 15, this is 30, this is 15. So I have shown this with a larger line, this one with a smaller line, okay? So both of them, it feels like that it is maximum at the center, and as we are moving away from the center towards the free ends, it is decreasing. Now, we considered a very appreciable part as a fiber. But if you want to do this analysis for extremely small fiber, for an infinitesimally small fiber, like any small element, what will happen? The value of this force F, which you got 15, that will become 0. It will keep on decreasing as you move away. Consider this section is a very small, very thin section, almost at the right end, almost which is equal to this area. So on that area, no shear force is acting, right? So there will be no force acting from the front side also. These are some of the concepts which we have already discussed, that how we consider such variations, how we increase the area. As we increase the area, more and more variation will be seen. If you decrease the area, the variation will decrease. The same exact manner we have analyzed so many different cases, right? So since this variation is going to be linear, for the rightmost fiber, for the extreme fiber, its value will be 0. Just like the value of shear stress was 0 at the top surface. If you recall the unit of shear stress in beams, on the top and bottom surfaces it was 0 due to the same funda. So for the right and left portion, it is going to be 0, right? And it is going to vary linearly like this. Same thing is going to happen in this bottom part also. If you start analyzing this bottom part, same thing will occur, but there will be one small change. What do you think? In the bottom part also, the force will act in this direction or force will act in this direction. Think about it. What is the basic difference between this part and this part? The basic difference is that this part is in tension. It is above the neutral axis. This part is in compression. As a result of that, the direction of net force will change. If you do this complete analysis, if you make this as compressive, both of them as compressive, you will get one value of F. That F needs to be balanced by the adjacent fiber, and that will be reflected in the cross section. The value and the direction of force that you will get, value will be same for the same area, value will be same if sigma 1 means if the maximum tension force is equal to maximum compression force, it's a symmetrical I section, then the magnitude of this force will be same, 15, but its direction will reverse. The same analysis we will conduct and you can conclude the same thing, but if you look at this direction, as I told you, it is going to get reversed. So in this part, again, the magnitude is increasing towards the center. This thing is still valid here. The magnitude is increasing towards the center, right? This is the magnitude that I have plotted. But you can see that its direction is opposite of the direction which was earlier, right? It is increasing towards the center. It is coming from the center. Now you will start getting a little bit feel of it. It feels like that shear stress is flowing. It is flowing like a fluid. In reality, it is not, but it feels like that it is flowing. You see, it is moving like this, and then it is moving out of it. Let's discuss about this web and then you will really be able to see that how the shear stress is flowing in this particular cross-sectional area. So we understood that how shear stress will vary for the flanges, these two flanges, right? Now let us see how it is going to vary in the web. So for that, consider the complete top flange, the complete top flange. Tell me how much units of force of F1 minus F2 will be acting on that. There are 1, 2, 3, 4, 5 different cuboids or 5 different fibers that I have shown for the top flange. In one, the force F1 minus F2 was 15, 1, 5. So in 5 of them combined, it is going to be 75. 15 multiplied by 5. So F1 minus F2 for the upper flange, for the top flange, is going to be 75. And some part of this section has to resist that F1 minus F2, right? And that resistance will be given by this section here, by the top area of this web, because let me demonstrate that using these two boxes. Suppose this part is the flange, this upper part, flange is this one, okay, is this one, okay, this part, and this vertical part here, web, is this one, okay. So this is flange, the upper part, and this is web. This flange is experiencing F1 minus F2 is equal to 75, okay. One part of this section needs to resist that. From where it can resist? From that same area through which it is contacting the upper part. Which is the area through which it is contacting the upper part? This area, this cross section, through which it is contacting the upper part. So this is the cross section, this same cross section which I have shown. This is that area, that web. This is the flange. So it needs to resist using shear force, which will be done by this area here, right? On this part, this bottom area, which is in contact with this web. So if this is the top flange, this part, this is the F1's direction, this is F2's direction, 75 units or F is acting in this direction, so it should be given a shear force in the backward direction, right? Because this F is along F1, so you need to give the shear force along F2. This is of 75 magnitude. Ideally, this now is 5 times of F, right? So on this flange, listen to me carefully. On this flange, the force, the shear force, which is acted by the web, should act in the backward direction along F2, right or not? So tell me that on the web, what will be the reactive direction of shear force? This one. Along this direction, this shear force will be reflected on the web. The very basic concept that we studied in the first unit of strength of materials, when we were understanding that, and in the mechanics also, that when we were understanding that how to show the action reaction for a given section, right? When we were studying about the deformation, so there we studied about these concepts. This is the same concept that I am referring to again. On the upper part, the force, shear force, needs to be given in the backward direction to resist F. So that force will be reflected here on the web on the front part, right or not? In other words, you can also understand it in a different way, that since F1 and F2, their resultant is along the F. If we are having F1 in this direction, F2 in backward direction, this is the web. So this resultant force F will be in forward direction. So on the web, it will be felt in the forward direction. This upper part in a way is trying to push it further. So on this part, it will be on the forward direction. This is another way to look at the same concept. So on this web, it is going to act in the forward direction. It is important. Direction is important, because if this is acting in the forward direction on F, on this part it will be coming in the upward direction. Use the same concept of complementary shear stress. If this is trying to rotate it like this will try to rotate it in the opposite way. So here the direction is going to be like this. And how much is this magnitude? This magnitude is now 75. right? Quite higher than these values. And as you will keep on going down, what is going to happen? Think about it. If I add one more fiber to it, what will happen? The value of F1 will further increase because it is still tension. In this fiber also tension is acting. If tension is acting, obviously the force will act in the same direction, right, as F1. So F1, F2 values, their difference will increase even more. One more value is going to get added here, right or not? So now if you look at it, that this section, flange plus some part of the web, that resultant F minus F2, that value will get even higher, right? So on this section, how much stress will act on this section? Let's say that one more fiber is gone now from here. So this upper part is gone now. Whatever is going to be the net force, F1 minus F2 due to this upper part, flange plus some part of web, will be coming in this forward direction, just like it was doing for 75 unit. And same will be reflected here. So the value of shear stress that is going to be present here is going to be even higher. Suppose this was 75, this value was 75, so this value will get even higher, let's say 84 it will become. But now the change will start to occur when you will start moving further down. Let's say the value was 84 up to this point where we considered one more fiber, right? But as you will keep moving down, when you will go just below the neutral axis, what will happen? The value of F1 minus F2 will start decreasing. Why? Because now compression forces are acting. Compression forces will decrease the value of F1 and F2, right? So that is why the value of shear force also, the resultant also that you will be getting, that will keep on decreasing as you start moving away from the neutral axis in the downward direction. So it is in the same direction, but it will keep on reducing. Once we do the analysis, this is what we are going to conclude. Now look at this diagram. Does it not look like that the shear stress is flowing like this? It is starting from some ends and moving in such a way that a fluid would move. If you will make some fluid move from here and from here, and if you give the fluid a channel to flow like this, this is how the fluid is going to move from here to here, and then it will divert. The discharge will divert. So in this case, the shear stress is compared to discharge. Obviously, it is not going to be in the exact same manner. The manner is going to change. You can see that in this region or in this region also, as we are moving ahead, the value of shear stress is increasing. Then again, it keeps on increasing till we reach at the centroid through which neutral axis is passing. And as we start moving away from the centroid, it again keeps on decreasing. So such a variation is called as shear flow. In reality, shear stress is not flowing, it's not a fluid, right? But that's how it looks like. The first conclusion that we can draw from this discussion, that these horizontal shear stresses, if you notice, they are cancelling each other. These shear stresses and these are in opposite direction. So effectively, there is no shear force in the horizontal direction, neither in the top flange nor in the bottom flange. So ultimately, the resultant shear force that you will get is going to act in the upward direction. From these values, these are the values of forces, right? You can know the value of shear stress by using the area. Shear stress is shear force divided by area. Using the area, you can do that calculation. We will discuss about that in the further topics. But please understand that there is no net horizontal shear stress due to these discussions. And obviously, why should it be there? If you recall the beam, we applied only the transverse shear stress, which was vertical. So there is no point that a horizontal resultant shear stress will come into the action. That P force is going to get resisted. That same P force that I showed a cantilever beam, a force P was acting. That P force is going to get resisted by these upward value of shear stresses. If you take the resultant force due to these, this will be equal to the applied shear force. They will totally cancel each other or totally balance each other. Clear? Horizontal ones are already balancing. So this is what you can write in the first point, that there is no net horizontal shear force. and the net vertical shear force here or net vertical shear stress here will be same as the applied shear force in the transverse direction or the applied shear stress in the transverse direction. Point number 2, if you notice, since we are calling it a flow due to an obvious reason that they are continuous, it is moving like this, arrows have to be continuous. You can never have such a system where you are having an I section like this. This is completely wrong because this is opposing the flow. It is trying to move here, then it should move up and then move out, but it is opposing the flow, right or not? So this is never possible. I have got some queries from the students where they have been told something else which is not correct. This is not possible. This is the correct way. The shear stress needs to flow in a definite way such that it looks like a flow of a fluid which is continuous, right? Please note one thing here, one thing where you should be careful about, which is true for other topics also. Whenever you are looking at action and reaction, be very careful. Which action am I talking about? Which reaction I am talking about? Which section I am taking for action and reaction? These things need to be carefully dealt with. Just like when I was drawing this part, I carefully showed you that how F will act, it will be opposed, then its reaction will come. If you do not do that correctly, then this direction will be reversed. And this is true for all the discussions or other discussions that we have done in earlier units. The direction is important. It can change your answer, it can change your marks, it can change your rank. Direction of shear flow also and the direction of preparation also, right? So it was a gyan, you can say, that is true for this also and for your preparation also. So be very careful about that direction. It is not to be written in conclusion, it is true in general for other topics also.